Hey logicians, this is Professor O, and today I want to talk to you a little bit about models, right, and how to determine truth and falsity. Coming up with a formal system about how to do this, right? All right, so I do have some review slides here. I'm going to have you just kind of look at those on your own. I'll have the slides online that you can link to. You can kind of check out what I'm saying here. Basically, what I want you to just understand is the difference between object and property, and how object and property is going to be represented in our language. So object names are going to be indicated by lowercase letters A through M in our textbook. Meanwhile, predicates are indicated by uppercase letters A, B, C through M. Okay, nothing else is, and then if you want to represent an atomic assertion, you place the predicate letter before the name. Right, so there are some examples. Right, you can kind of just check those out. This is how you would translate them into English from the notation. All right, this stuff isn't super important, okay, but I just want you to kind of know that that's how things look, you know, and so you can just kind of revisit that, right? Let's talk a little bit about recursive definition of CL star. Right, our alphabet consists of two predicate letters, F and G. So we're going to keep things kind of simple here. We're not going to worry about A through M just yet. And we're going to just worry about A and B as names. Okay, so we'll only have like single little names. That'll be nice. All right. Now, we'll have a couple rules about how to push this alphabet around. What we want to do here is follow this one. Any predicate followed by a name, and we're going to make that a single name, is a well-formed formula of CL star. Okay. We'll let P and Q be any well-formed formula. Remember the little P and Q, those are just variables. Okay, they stand in for anything. Then the expression P arrow Q is well-formed as well, and nothing else is. Right, so that kind of gives us our syntax rules. The semantics of CL star assumes the same semantics for CL. Okay. Now, if you remember in that language, what we said was that a conditional P arrow Q is false if and only if its antecedent is true and its consequent is false. Otherwise, the conditional is true. Right, it's very important. Now, here is a little thing that I want to introduce you to. This is a little device. It's kind of handy. We call this a truth table. And this signifies a comprehensive way that organizes all the different possible ways that we could interpret P and Q. Both P and Q could be true, right? And so it comes out true. P could be false, Q could be true, it comes out true. And P could be false and Q could be false, and it comes out true, right? The only time it ever comes out false is if P is true and Q is false, okay? So that little pattern TFTT is kind of helpful to remember. Now you might be wondering as an English user, why on earth, how on earth could, a sentence that's got, like an if P then Q style sentence, why would that be true if the antecedent's false? That doesn't seem right. It doesn't seem like you should be able to get the truth out of a falsehood. Well, you can't think of it that way, right? You have to think of it as conditional, right? So think of it like, if it's raining outside, then it's wet outside. Right, now that's going to be true regardless or not if it's raining outside at all. Now the streets might be wet because, I don't know, people might have the fire hydrants opened up and there's water everywhere. But it's still going to be the case, right, that if you say, if it's raining outside, then it's wet outside, it's going to be true. Okay, the only time a claim like that's going to be false, if for whatever reason it's raining outside, but it's not wet outside. Okay, now I don't know what kind of world that would be, but just, that's a little primer for why it's kind of interpreted that way, so just kind of keep that in mind, right? All right, now we need a little bit more for CL star. That's good enough for kind of interpreting the conditional, right? But we need a little bit more about how to figure out whether or not A is F is true. Right, and how are we going to do this? And the answer to that question is by use of models. Okay, now what the heck is a model? Answer: it's the way the world would have to be like if A is F were true. Right? It's the way the world would have to be like if A is F were true. All right, so let's just take the statement, right? The cat is on the hat, right? To say that the cat is on the mat is just to pick out all the ways the world will have to be for the cat to be on the mat. So you need some particular cat, a particular mat, and a definite meaning of on, and then a physical space where the cat is on the mat. I'm feeling like this music is a bit too loud. Just a second here. All right, we are back. Okay, so particular cat, particular mat, definite meaning of on, and a physical space where the cat is on the mat. Now, the ways the world could be are formally represented by models. Okay. Models then tell us which atomic assertions, if any, are true. Right? So here's the thing you kind of have to understand about logic is that as logicians, as we operate as logicians, we are not doing any kind of investigation. Right? We're not inquiring into the way the world is at all. What our job is to consult a model. Right? The model will tell us what's true and what's false. Right? That's basically it. Okay, I know it's not that interesting in terms of like, well, what's really the case and all that kind of stuff. What we care about is just whatever the model's telling us, and then we figure out what is implied from there. All right? Okay. So if the atomic assertion then satisfies the model, it's true. But if it doesn't satisfy the model, then it's false. Okay, that's the big idea here. The model is just telling us what's true and false. Does the assertion satisfy the model? Okay, got to figure that out. And if it doesn't, right, it's false. If it does, it's true, right? Now remember, models are a feature of every language. We're going to use L. Now, I think in another lecture, I had a nice curly Q scripted L to refer to an arbitrary language. For some reason, it turned to Comic Sans, so I apologize for that, but there you have it. We're just going to use L to refer to just any language that we can cook up, like CL or CL star, any kind of formal logical language, right? So when we have that in mind, right, we can say then, for any formal language, a model for the language is just any specification of the truth value for every atomic well-formed formula in the language. Okay, so that's what a model is going to do. So you have like a sentence in some formal language. It's made up of, I don't know how many atomic formulas. You have a model, right, for that language if and only if you have a truth value specified to every atomic formula. Okay, so look, if this is not kind of making sense, let's just kind of return to CL, right? The nice simple language that only has 2 sentence letters, P and Q, and 1 connective. All right. So what you got here then is the little truth table. Now notice that we have all 4 possibilities the way the world could be, right? P and Q could both be true, right? Q could be false and P is true. Then we have P being false and Q true, and then they're both false, right? Those are the 4 possible the ways the world could be. Right, and then you can go on to interpret what if P then Q might mean, right, given those 4 ways. Okay, now this is just a little bit of notation in the book. These are called functions, right? We have R1 and R2 and R3 and R4. Okay, those are functions. They're like input-output devices, and if you input a P on R1, you get a T. If you input a Q on R1, you get a T. And so then that's what ends up kind of filling in, right, the rows in the truth table here. So R2 takes as input a P, you get a T. Takes as input a Q, you get an F, all right? It's kind of overkill, all right, but that's basically the idea. This is kind of stated in the textbook. So, just be mindful of that. Not super important, okay? All right. CL star is a bit more complicated. Here we have two names, A and B, and 2 predicates, F and G. Now, how do we construct a model for those guys? Right? What do we do there? Right? The answer goes like this, right? What we got to do is specify a set of objects, right? So that's the first thing we got to do. Then we got to specify which of those objects belong to each of the two predicates, right? So you got your objects, and then you have to tell us, like, what objects belong to the two predicates. Then you got to specify which of the objects are labeled by each of your two names. Okay, so the procedure basically consists of this, right? We come up with a set of objects, we just specify it, and we call that the domain, D, all right? Then we introduce a function, and we're going to use the Greek letter pi to indicate our predicate function that will take as input any predicate from CL star and give as output a subset of the domain. And just note that the subset can be identical with all of the objects in the set of the domain, right? Subsets are always a part of sets. Okay, it's like a rule of set theory if you didn't know, right? Okay, and then we're going to introduce a function using the Greek letter tau called the term function that takes as input any name from CL star and gives as output a single member of the domain. Note, single member, okay? All right, so here is an example, all right? Here we are going to be talking about the cities of Austin and Boston, so that's going to be our domain, right? Our domain of discourse, it is sometimes called. And then we are going to introduce a predicate function. Here we have Austin, which is in the extension of F. Okay, so Austin is in the extension of F. All right, it's whenever Austin just goes with F basically. Okay, G is a little bit different here. Austin and Boston are in the extension of G. Okay, so G can be attached or attributed to Austin and Boston. All right. Then, of course, our names, as you might have guessed, right? A is going to go with Austin and B is Boston. All right. So with that framework in mind, we can say that A is F, A is G, and B is G are all true. Now, here is why. Let's take a look at this. All right, let's take a look at this, okay? A is F. One way of saying that in a real technical way is to say A is in F. A is in F. Well, what is A naming? Austin. Is Austin in the extension of F? Yes, it is. It satisfies the model, right? It satisfies the model. Then, what about this? Is A in G? Well, it sure is. Austin is in the extension of G, and so is Boston. B is naming Boston, and so it's in G. Okay, so those are all true, right? Those satisfy the model. Okay. By contrast, though, B is F is false because Boston here, B is naming Boston, is not in the extension of F. It's not there. Only Austin is. Okay, so that's false. Okay. Now, some things to note. The domain is a collection of things, so it's indicated by sets, right? It's indicated by curly brackets. Same things with predicates. They have extensions. They're also indicated by the curly brackets, right? The curly brackets, when you see that, you should think set, all right? And believe it or not, this right here is a set, okay? Right now it's empty. There's nothing in it. But there is such a thing as the empty set, okay? Just think of the set of all the unicorns in the world. That is a set. It is empty, okay? There's no unicorns in it, right? But there is a set, and it's called the empty set, right? Predicates are sets as well because they have extensions, all right? Now, the only thing that's a little different here, a little weird, is that terms have reference, right? Reference can only reference can only be exactly one thing, all right? Exactly one thing, all right? So there is no set there, okay? You can't have a name referring to more than one thing. If a name does that, then it fails as a name, okay? Now, I know that there are people, right? Like I've had classes where there's more than one Adam. That's the case, right? So, well, isn't the one name Adam referring to two people? And the answer is yes and no. Really, though, what's happening is that there's two names that go by the name of Adam. Okay, so this is kind of weird. What you have to somehow distinguish them, like Adam 1 and Adam 2, right? That's going to refer to me and then some other kid in the class or something like that. Okay, and we do this all the time. So whenever there was 2 Adams in the class, right, we'd say, well, we'll call you Adam O, and the other guy Adam A, or something like that. Okay, and so that way then we can kind of figure out what's going on. Okay, because this is how names work. We want names to kind of just designate one thing, right? Okay, so to refer to our models generically and formally, we're going to use the following notation. M is for model, and that equals, right, this ordered set of items that include the domain of discourse, the predicate function and the extensions that it specifies, and then the term functions and the reference that it specifies. All right, some more things to note. The domain may contain things that are not referred to by any name. Yes, this can be the case, right? There are stars in the universe that we haven't named, okay? That's how it goes in life. 2 predicates can have the same extension. Absolutely, that's right. So think of the predicate triangular, and then think of the predicate trilateral, okay? Those are 2 different predicates. We're talking about 3-sidedness and then 3-angledness or whatever, okay? And what's going to be in the sets of what's, the members of those extensions are going to be all the triangles, right? All the triangles in the world populate the extensions of those predicates, right? Okay. The extension of a predicate can include everything in the domain. That's right. Yeah, that's right. There's no reason why the extension of a predicate has to be smaller. Okay, so that's just something to remember. All right, 2 names now can have the same referent. Okay, so like I said before, right, we don't want a name having 2 referents. Okay, that doesn't work. But 2 names can have the same referent. All right, so you think of Muhammad Ali. That's a name that refers to the same person that the name Cassius Clay referred to, okay? And you can multiply examples like this, right? Well, now I can't think of any, of course. I think the classic example is Hesperus and Phosphorus, right? That's the names for the morning star, which just turned out to be Venus, Venus with a V. Venus with an M. I don't know what I'm thinking today. Anyway, there you have it. 2 names can have the same referent, all right? Okay, just think of this. A semantics for any formal language L requires us to do 2 things, right? We need to define what counts as a model for the language so that every distinct model represents the way things could be for the language. And then we need to define truth in a model, which tells us how to determine the truth of the well-formed formulas in the language, okay? So what this is basically saying is that, hey, I got a language, how do we tell whether or not it's true? Okay, so we need some kind of device that figures out what's true and false for us. Okay, because again, our job as logicians is not to figure that out. So what counts as a model then has to be specified so that we can kind of figure out then what to consult, right? Then to define truth in the model, we have to figure out how to determine, whether or not the thing is satisfied or not. Now, it was kind of intuitive for the, what we just looked at. Well, was the referent of the name in the extension of a predicate? And then if the answer was no, well, then it was false. If it was true. Okay. All right. Let's talk about semantics of CL star. All right. All right. We're going to let M be a model that has a domain of discourse, predicate function, term function. An atomic formula is true in M if and only if the referent of the name is in the extension of the predicate. And then, of course, a compound formula is false, the antecedent is true, and the consequent is false. And it is true if and only if either the antecedent is false or the consequent is true. Okay, so that just reflects our truth table. So what you need to remember here, okay, is this bit right here. Okay, that's important, and then you need to just, crud. Let's, there we go. You need to memorize that bit right there, and then memorize this right there. Okay, and that's going to be your job as logic students for today. Okay, you need to really understand that. Okay, there are some practice problems here you can go through if you'd like. Right, check those out on the slides. Here are the answers. Right, and then the last thing I wanted to do here. Let's see if I can get out of PowerPoint and actually go over some of the homework for you here. Let's see if I can pull this up. Okay. So there's homework 2. That's going to be due, and I'm going to try to make this bigger. There we go. Okay. Now, what's going on in this homework here, right, is just kind of some review work, right? You're breaking down the atomic formulas, all right? And notice here, we're not going by CL star, or wait, we are going by CL star here. So you have to determine whether or not stuff is well formed. Okay, is stuff in the alphabet? All right. Remember CL star, right? It only has one name, not 2. Okay, so don't be confused by that. All right, so figure those out. All right, and then now here in number 3, this is where it gets a little confusing. Okay, you might be thinking, hey, wait a minute, were we going with CL star? And the answer is actually no. Here we're using the notation of the book. Okay, so what I want you to just realize is that this is all okay. All these are well formed, right? So you might be thinking, what on earth is that? All you have to do is just kind of put this over here in the sub formula, okay, because it doesn't have any compounds, right? So if you're confused by that, I just wanted to clarify this is not reflecting CL star, while this one is. Okay, I wanted to go over that because it can be kind of confusing. Right, then what you got to do is just figure out whether or not, according to this model, right, these claims are true or false, and then you need to explain why in each case, right? In each case. And I guess it goes like that. Okay. All right. So then, yeah, write down something that's different than anything that's giving that's true. Then write down a compound formula, right, that is false. And so what you got to do is come up with a formula that has a true antecedent and a false consequent. Okay, and then you just kind of go through that sort of issue here. And again, you're judging that by this model here, right? So this model right here is governing the questions, right, up till about C. And then in D, you got to come up with your own model then, which will make this false. So you got to make a true antecedent, false consequent, and then go from there. Here you can make one true. That's pretty easy. You have 3 different ways you can do it. And then you got to come up with a model that makes this one true and this one false. All right, so I hope that helps a little bit. Always reach out to me. I try to answer your emails or your Google chats as fast as possible. And I think that's it for today. So I will talk to you later.